Last time we derived these two pairs of equations for geometrical optics, and they will be the foundation for this lecture. In studying the passage of beams of rays through optical systems, special interest is related to bundles whose rays all pass through one point, and such bundles are said to be homocentric. After passage through an optical system, homocentric bundles in general cease to be homocentric, which means that after passing through a body, the rays will no longer come together at one point. Only in exceptional cases will the rays starting from a luminous point come together after passage through an optical system and all meet at just one point. The most important case where there is an approximate transition of homocentric bundles into homocentric bundles is that of sufficiently narrow beams, that is, beams with a small opening angle, passing close to a particular line for a given optical system. This line is called the optic axis of the system. Nevertheless, we must note that even infinitely narrow bundles of rays in the three-dimensional case are in general not homocentric. Even in such a bundle, different rays intersect at different points. This phenomenon is called astigmatism, and we can sketch this situation like this. So we have some kind of surface, a very small element of surface, and here we have the point B, here we have the point A, C, D, and the rays that pass through the points B and D will intersect at some point that I will call O2. So this intersection will depend on the radius of curvature that I will call R1 of this surface. An element of surface is characterized by two radii of curvature, one like this and one in a perpendicular direction here, which let's say contains the points A and C. So A and C will intersect at a different point in general, that here I will call O1, and this radius of curvature will be R2, for example. So maybe I could have called this one R2 because I have called this point O2, and this one will be R1. But the substance or the core of the matter doesn't change. That's still the same thing. So you can see that even for very small surfaces, we have two different points here. So these bundles are not homocentric. The exceptions are those points of the wave surface at which the two principal radii of curvature are equal. So a small region of the surface in the neighborhood of such points can be considered as spherical. And therefore, in this case, narrow bundles of rays will be homocentric. And we will consider now an optical system having axial symmetry, and the axis of symmetry of the system is also its optical axis. The wave surface of a bundle of rays traveling along this axis also has axial symmetry. As we know, surfaces of rotation have equal radii of curvature at their points of intersection with the symmetry axis. Therefore, a narrow bundle of light moving in this direction remains homocentric. To obtain general quantitative relations, determining image formation with the aid of narrow bundles, passing through an actually symmetric optical system, we use the general equations that we derived last time. It's these two set of equations, these two pairs, and we will use these general equations after determining first of all the form of the function chi in the case under consideration, which is axial symmetry. Since the bundles of rays are narrow and move in the neighborhood of the optical axis, the vectors n and n prime for each bundle are directed almost along the axis. If we choose the optical axis as the x-axis, then the components ny, nz, n prime y, n prime z will be small compared with unity. So they will be small compared with 1, much smaller than 1. As for the components nx, nx prime, we will have nx approximately equal to 1, and nx prime will be approximately equal to plus or minus 1. In the first case, the rays continue to travel almost in their original direction, emerging into the space on the other side of the optical system, which in this case is called a lens. So in the case where we have a plus, whereas if we have a minus, the rays change their direction to almost the reverse. Such an optical system is called a mirror. For the minus here, we will have a mirror. Making use of the fact that ny and z, ny prime and z prime are small, we can expand the angular iconal chi in series. and stop at the first terms. Because of the axial symmetry of the whole system, chi must be invariant with respect to rotations of the coordinate system around the optical axis. From this, it is clear that in the expansion of chi, there can be no terms of first order, proportional to the first powers of the y and z components of the vectors n and n prime. Such terms would not have the required invariance. The terms of second order, which have the required properties, are n squared and n prime squared, and also n dot n prime. Thus, to terms of second order, the angular iconal of an axially symmetrical optical system has the following form. Chi will be a constant plus some other constant g, which we will divide by 2 just for the sake of convenience, times ny squared plus nz squared plus some other constant f times ny prime plus nz prime. So this is just a dot product between n and n prime, but we are simply considering the two components ny and nz, because remember that chi depends only on the independent components, which are ny and nz, because we are assuming that the norm of the vectors n and n prime are just equal to 1, and we can write nx prime and nx as functions of ny and z and ny prime and z prime. Then similarly we have plus some constant h over 2 times ny prime squared plus nz prime squared, and f, g, h are just constants. In order to define our equations properly, we have to choose a sign here between the plus or the minus for nx prime. We shall assume that nx prime is equal to plus 1, meaning that we are considering the case of a lens. For a mirror, it is possible to see that all the formulas have a similar appearance. It's possible to show that. Now, anyway, substituting this expression here into this pair of equations, so we just have to take these simple derivatives, we can rewrite our pairs of equations like this: ny times x minus g minus f ny prime equal to y. Then we have nz times x minus g minus f nz prime equal to z. Then we have f ny plus ny prime x prime plus h equal to y prime. And then we have f nz plus nz prime x prime plus h equal to z prime. We consider a homocentric bundle emanating from the point xyz, and let the point x prime, y prime, z prime be the point in which all the rays of the bundle intersect after passing through the lens. If the first and second pairs of these equations were independent, then these four equations for given x, y, z, x prime, y prime, z prime would determine one definite set of values for ny and z and ny prime and z prime, which means that there would be just one ray starting from the point xyz, which would pass through the point x prime, y prime, z prime. In order that all rays starting from the point xyz shall pass through x prime, y prime, z prime, it is consequently necessary that these equations are not independent. That is, one pair of these equations must be a consequence of the other. The necessary condition for this dependence is that the coefficients in one pair of equations be proportional to the coefficients of the other pair, and therefore you can check that we must have x minus g over f equal to minus f over x prime plus h equal to y over y prime equal to z over z prime. In particular, we can also rewrite the following equation: x minus g times x prime plus h equal to minus f squared. The equations we have obtained give the required connection between the coordinates of the image and object for image formation using narrow bundles. The points x equal to g and x prime equal to minus h on the optical axis are called the principal foci of the optical system. Let's consider bundles of rays parallel to the optical axis. The source point of such rays is clearly located at infinity on the optical axis, which means that x is equal to infinity, because these rays are parallel to the optical axis, so they will have to come from infinity. From this equation, in this case, we see that x prime must be equal to minus h. Therefore, a parallel bundle of rays after passage through the optical system intersects at the principal focus. Conversely, a bundle of rays emerging from the principal focus becomes parallel after passage through the system. In this equation, the coordinates x, x prime are measured from the same origin of coordinates, lying on the optical axis. It is, however, more convenient to measure the coordinates of object and image from different origins, choosing them at the corresponding principal foci. As positive direction of the coordinates, we choose the direction from the corresponding focus toward the side to which the light travels. Designating the new coordinates of object and image by capital letters, we have capital X equal to x minus g. Then we have capital X prime equal to x prime plus h. And then we have capital Y equal to y. And then we have capital Z equal to z. And capital Z prime equal to z prime. And therefore, the equations of image formation in these new coordinates take the following form. We have capital X times capital X prime equal to minus f squared, and y prime over y equal to z prime over z equal to f over capital X equal to minus capital X prime over f. So we can rewrite these equations also in this form. The quantity f is called the principal focal length of the system. The ratio y prime over y is called the lateral magnification. As for the longitudinal magnification, since the coordinates are not simply proportional to each other, it must be written in differential form, comparing the length of an element of the object along the direction of the axis with the length of the corresponding element in the image. So from this equation, we can write the differential of x prime with respect to the differential of x. This is simply equal to f squared over x squared, and it is also equal to y prime over y squared. From this, that even for an infinitely small object, it is not possible to obtain a geometrically similar image. The longitudinal magnification is never equal to the transverse, except in the trivial case of identical imaging. A bundle passing through the point capital X equal to f on the optical axis intersects once more at the point x prime equal to minus f on the axis. These 2 points are called principal points. From these equations here, let me show you these 2 pairs here. We can see that in this case we have the equations ny equal to ny prime and nz equal to nz prime, because we can rewrite in this case ny times capital X minus f ny prime equal to capital Y. So this is one of those equations, those pairs of equations, in particular this one. And then we also have this one here, which we can rewrite in a similar fashion. So let me rewrite it below. We have nz times capital X minus f nz prime equal to capital Z. And since we are on the optical axis, we have the condition x equal to f, and also y, capital Y equal to capital Z equal to 0. And therefore, from here, we get trivially those 2 equations. Therefore, every ray starting from a principal point crosses the optical axis again at the other principal point in a direction parallel to its original direction. If the coordinates of object and image are measured from the principal points and not from the principal foci, then we can write 2 coordinates, xi prime equal to capital X prime plus f, and then we can define also xi equal to capital X minus f. And if we substitute these 2 equations here, let me show you, into this expression here, capital X times capital X prime equal to minus f squared, it is easy to obtain the equations of image formation in the following form: 1 over xi minus 1 over xi prime equal to minus 1 over f. One can show that for an optical system with small thickness, for example a mirror or a thin lens, the 2 principal points almost coincide. In this case, this equation here is particularly convenient, since in it xi and xi prime are then measured practically from one and the same point. If the focal distance is positive, then objects located in front of the focus, capital X greater than 0, are imaged erect, which means that y prime over y, capital letters, is greater than 0. Such optical systems are said to be converging. If f is less than 0, then for capital X greater than 0, we have y prime over y less than 0. You can see that from the equations that we derived here, for example. And in this case, if y over y prime is less than 0, the object is imaged in an inverted form, and such systems are said to be diverging. There is one limiting case of image formation which is not contained in the formulas that we have derived. This is the case where all three coefficients f, g, h that we defined previously are infinite, which means that the optical system has an infinite focal distance and its principal foci are located at infinity. Going to the limit of infinite f, g, and h, we can rewrite one of the equations that we derived, in particular this one, let me see, this one here. We can rewrite this equation simply like this, so we can multiply the terms. We have x prime plus x times h minus g x prime minus gh equal to minus f squared. But if the coefficients are very large, this term here can be neglected, and therefore we can rewrite our equation like this: x prime equal to h over g. This multiplies x plus f squared minus gh over g. Since we are interested only in the case where the object and its image are located at finite distances from the optical system, FGH must approach infinity in such fashion that these ratios that you see here, this ratio here, h over g, and this ratio here, are finite. Denoting them, respectively, by alpha squared and beta, we can write x prime equal to alpha squared x plus beta. And for the other two coordinates, we now have from the general equation that we wrote earlier, from this equation here, so you can see it written here, but you can replace y prime and y here, so the lowercase letters, and basically dx prime over dx can be obtained also here, even if these are lowercase letters, because after all, x prime is just proportional to capital X prime. There is just a constant between them, so the differentials are the same. So the differential of capital X prime is equal to the differential of lowercase x prime, and similarly for dx, this is equal to d capital X. And therefore you can see that y prime over y is equal to z prime over z, which is equal to plus or minus alpha, right? Because we know that y prime over y squared is equal to alpha squared, this coefficient here, because it is simply the derivative of x prime with respect to x. Finally, again, measuring the coordinates x and x prime from different origins, namely from some arbitrary point on the axis and from the image of this point, respectively, we finally obtain the equations of image formation in the simple form capital X prime equal to alpha squared capital X, and then we get y prime equal to plus or minus alpha capital Y, capital Z prime is equal to plus or minus alpha capital Z. So in this case, when lowercase x is equal to 0, we know that lowercase x prime is equal to beta. So we simply define capital X prime as x prime minus beta. So if you rewrite this equation as x prime minus beta equal to alpha squared x, from here you will simply get to this equation here. Therefore, the longitudinal and transverse magnifications are constants, but they are not equal to each other. And this case of image formation is called telescopic. All the equations that we derived for the lenses apply equally to mirrors, and even to an optical system without axial symmetry, if only the image formation occurs by means of narrow bundles of rays traveling near the optical axis.